Hi, in this video we're going to talk about simplifying trigonometric expressions by using trigonometric identities. Now recall that by definition we know the following: tangent theta, cotangent theta, secant theta and cosecant theta. Now you can notice here that cotangent theta is also the reciprocal of tangent, so I can write this as 1 over cotangent theta. Now these are the expressions we know by definition. Now we have two trigonometric identities we need to know so that we can simplify expressions or prove statements. These identities are 1 plus tangent squared theta is the same as secant squared theta, and 1 plus cotangent squared theta is equivalent to cosecant squared theta. Now these identities are not by definition, these have to be proven. So let's quickly prove them. To start with, we know that sine squared x plus cosine squared x is 1. Now if I divide both sides by cosine squared x, we can then write this one as tangent squared x because it's sine over cosine, plus, well, they simplify out to 1, and 1 over cosine squared x is secant squared x. So that's how we quickly prove it. And similarly, to prove 1 plus cotangent squared x is the same as cosecant squared x, we again start with sine squared x plus cosine squared x equals 1. But then we divide all sides by sine squared x so that we get 1 from the first expression plus, because they simplify each other out. The second one will be cotangent squared x, and on the right hand side it's going to be cosecant squared x. We could also use direct proof. I'm going to show the steps only for this expression. So we can start with 1 plus cosine squared x over sine squared x instead of cotangent. And then we can say, okay, this is 1 over 1, so we have to equate denominators. So we will expand it by sine squared x. So it's going to be sine squared x plus cosine squared x at the top over sine squared x. Well, the top part is 1 as we know, right? So it's going to be 1 over sine squared x, which means cosecant squared x. You can also show that these two expressions are equivalent. Now let's see some examples. Prove that cosecant to the power of 4 of x minus cotangent to the power of 4 of x is equal to 1 plus cosine squared of x divided by 1 minus cosine squared of x. Now we have to notice that the left-hand side expression is difference of squares, because this is cosecant squared of x squared and this is cotangent squared of x squared, and there's the minus sign in between, so we have to factorize accordingly. So we're going to write cosecant squared of x minus cotangent squared of x times cosecant squared of x plus cotangent squared of x. Now we know this identity, but knowing is not enough. We have to be able to play with this, like taking cotangent to the other side. It's going to be cosecant squared of x minus cotangent squared of x, which is 1. So here, this expression actually is 1. So I end up with only this factor, which is cosecant squared of x plus cotangent squared of x. Now it's time to write their equivalent by definition, which are 1 over sine squared x plus cosine squared x over sine squared x. So this means we can write this as one single fraction like this. But now the problem is we don't have this here. We have sine squared x, but we know that sine squared x plus cosine squared x is 1. So again, we have to play with this, taking cosine squared x to the other side. So it's going to be sine squared x equals 1 minus cosine squared x, which I'm going to write here. So this expression will be 1 plus cosine squared x over 1 minus cosine squared x. Another example. Given that tangent of A is minus 5 over 12 and the angle A is obtuse, find the exact values of secant A and sine A. Now, first of all, let's look at this word obtuse. Now, this gives me that on the unit circle, this angle is either this or this, because at quadrant 2 and 4, tangent is negative, right? But we're told that the angle is obtuse, so we'll go with this one. Now, since 1 plus tangent squared A would be secant squared A, I'm going to substitute the values. So it's going to be 1 plus minus 5 over 12 squared, and this will give me 1 plus 25 over 144, which is 169 over 144. So when I take the square root, I'm going to find secant A to be plus or minus 13 over 12. Now, which of the values am I going to choose? I know that the angle is obtuse, and in the second quadrant, just because secant A is 1 over cosine A, and I know that in the second quadrant cosine is negative, 1 over cosine must also be negative, which is the secant. So I should be picking the secant A to be minus 13 over 12. So the use of the unit circle is very important here. Now for sine A, I have to use tangent A equals sine A over cosine A. Now I know tangent A, so it's good, but I don't know cosine A. However, I know secant. So just because secant A is 1 over cosine A, if you flip these expressions here, it's going to be cosine A equals 1 over secant A, so 1 over minus 13 over 12, which is minus 12 over 13. Now that I know these two, I can find sine A, because sine A now will be tangent A times cosine A, which will be minus 5 over 12 times minus 12 over 13, and the result will be 5 over 13, because these will simplify each other, and minus times minus is plus. So the answer to sine A is 5 over 13. Another example. So simplification questions are another form of proof questions. In proof questions you have the answer given. In simplifications you don't. So let's start with the first one. It's sine theta, cotangent theta, and secant theta. I'll rewrite this expression as sine theta times cosine theta over sine theta times 1 over cosine theta. And as you can see, these cancel each other out, leaving us with 1 only. Whereas in the second one, I have to start with the brackets first, so I rewrite it as sine theta, cosine theta, so these are in multiplication obviously, 1 over cosine theta, that's what secant is, plus 1 over sine theta. And when I started learning these for the first time, I was wondering, why didn't they just say cosecant to be 1 over cosine, so that it would be easier to remember? But, well, now it's also easier to remember that it's going to be the opposite. Yeah, secant is for 1 over cosine and cosecant is for 1 over sine. Right, after this, we just equate the denominators and get this expression, and obviously the denominator here simplifies with this product here, and you end up with sine theta plus cosine theta as your answer. One more example. Prove that this expression on the left-hand side is equivalent to cosine cubed theta. Now, let's start writing these by the definition. So it's going to be cosine theta over sine theta for cotangent theta times for cosecant, I'm going to write 1 over sine theta, and in the denominator it's going to be 1 over cosine squared theta plus 1 over sine squared theta. Now, if I do the multiplication in the numerator, I'm going to end up with cosine theta over sine squared theta, And in the numerator, I have to equate denominators to end up with sine squared theta plus cosine squared theta over sine squared theta times cosine squared theta. And this is actually cosine theta over sine squared theta over 1, because sine squared theta plus cosine squared theta is 1, over sine squared theta times cosine squared theta. Now is the time to convert this division into multiplication. And if we start simplifying, sine squared thetas are gone, and we're going to end up nothing but cosine cubed theta. So that is shown. Or in Latin, QED for quaderat demonstrandum. So it's all about playing with the definitions, converting them from one expression to another, and simplifying them. And in the proofs, generally we play with the left-hand side, but sometimes be cautious that you may need to play with the right-hand side as well. And also you should be flexible. Just because it's a sine squared theta plus cosine squared theta, it doesn't mean that I'm going to use it like that to end up with 1. Sometimes I might need sine squared theta written in terms of cosine squared theta, so I have to consider sine squared theta equals 1 minus cosine squared theta, taking it to the other side. So try to be flexible with those trigonometric identities. Thanks for watching.